Okay, good morning. Thank you for coming. Thank you for your patience while we dealt with various technical difficulties. It's always amusing and at least entertaining to give a talk that involves two laptops. I've lost count myself. All right. So this talk is a bit about Java today, but it's also an attempt to peer into the future to try to see what's coming down the road. I will do several demos. I'll probably mistype something. If you see me make a mistake, please shout out to correct me and help me out up here. Questions are okay during the demos, but this isn't meant to be a Q&A, at least until the end. We have time at the end. Happy to take questions there. I would like to start with the canonical set of polls. How many people are using Java 8 in production? How many people are using Java 11 in production? Yay, good. How many people are at least using a release later than 8 in development? Trying it out, kicking the tires. How many people have downloaded Java 12 and are doing something with it? Okay, that's pretty good. By the end of this, I hope to convince more of you to go and do that, even if you don't use it in production. At the very least, download 12, even download 13, and try it out and send us feedback on some of the new features. All right, before we look at specific features, let's first kind of just remind ourselves a bit. How is it that we decide to add things to Java? Do we just add stuff to keep up with the cool kids, or add stuff to keep it appealing no matter what? No, of course not. What does drive Java forward? For almost 24 years, Java's been driven by two big goals. That'll be 24 years on the 23rd of this month, by the way. Two big goals. The first is developer productivity. Java is about helping developers build and maintain large and reliable programs. Yes, sometimes people complain that the language is a bit verbose, but that verbosity, to an extent, has an advantage because it means the code that you write today, you will be able to understand a year from now. Somebody you've never met will be able to understand it 10, 20 years from now. Java isn't about writing one-off scripts. It never has been. It's about building things for the long haul and being able to maintain them for the long haul. The other big goal for 24 years has been program performance. Performance, of course, we measure in many different ways. We measure time in the form of startup time and latency and throughput. We measure space, both static space of a system in storage, of a dynamic space in terms of memory consumption. We measure scalability in a bunch of ways. We like to talk about Java working from iPhones to Big Iron and actually making that a real thing, which, well, it kind of is. For almost 24 years, we've pursued these two big goals in the face of constantly evolving factors. And this is part of what makes working on Java itself fun. It's also what makes working on it a real challenge from time to time. Things are always changing. Programming paradigms are changing. People are more interested now in mixed functional and object-oriented programming. Data-oriented programming is becoming a thing. Application areas are changing. We have big data and machine learning, which a lot of people want to do in Java, but Java isn't doing as well for them as it could, so we're working on ways to make that better. Deployment styles are changing. We used to talk about jar files, loaded into web browsers and security managers and all this other stuff. But guess what? Java apps and web browsers are not a thing in this decade of this century. But Java is being used to deploy applications in clouds, into packaged applications that wind up in app stores and things like that. And of course, hardware is always evolving. We now have machines with terabyte memories. We have deeper memory hierarchies with lots of caches between your processor core and your memory system. We have deeper and more numerous processor pipelines. And we have vector and SIMD instruction sets, both on sort of what are now considered normal processors, and then the really souped up ones that you find in GPUs. So we're pursuing these two big goals in light of all these factors in some of the major active projects in the OpenJDK community, and that's what I'd like to talk about today. So the ones I will discuss are Amber, which is about right-sizing language ceremony, reducing some of that boilerplate in effect. This is being led by Brian Getz. Loom, bringing continuations and fibers to the Java platform. This is being led by Ron Pressler. Panama, a new foreign function and foreign data interface, being led by Maurizio Chamada-More. And finally, Valhalla, the big one, value types and specialized generics for the Java platform, being co-led by John Rose and Brian Getz. So let's start with Amber. So Amber is aimed squarely at the pain point that Java requires too much ceremony. There's just too much boilerplate. How many people like the amount of boilerplate in Java? 1, 2, oh, okay. Well, you're the humor guy, of course you like. And this just gets especially painful when you're trying to do microservices that are just going to exchange some data in and out, and you have to deal with all these verbose classes. And just why? Let's make it better. So the Amber solution is actually we're not attacking boilerplate directly, right? We could attack boilerplate directly by transforming the Java syntax into something like APL, and then all your programs would be really dense and compact, and there would be no boilerplate, but they would also be unmaintainable. Rather, the approach we're taking is creating a series of language features over time, delivered over time. They work together that let you express more clearly what you mean. And if you can express more clearly what you mean, then the boilerplate will take care of itself. There will be less of it. There will still be a little bit probably, because that's just the way Java is. All right. How many people were in Trish's talk just before this one? Okay. I couldn't be here, so I'll ask you, and I'll dynamically optimize this talk as we go. Did she talk about local variable type inference? Yes? A little bit? Should I talk about it? Yes. Okay, fine, I'll talk about it. All right. Type inference. Does Java have type inference? Yes? No? Did it always? Okay. So, a lot of people think Java doesn't have type inference or never really had it until like just recently or something, but it's actually had type inference for a long time. Back in Java 5, when we did generics, when we added generics, we could have made you write the generic type of the return type of every method invocation. So if you want to invoke collections.emptylist, you would have to type string in pointy brackets to indicate the return type. But that would have been dumb, so we didn't do that. The compiler has all the information that it needs to determine that, well, the string is the return type in this case, so you don't have to write that. You can if you want, but I've never actually seen anyone do that. In Java 7, we introduced a thing called the diamond operator. List of string, list equals new array list string. Here you're typing string in pointy brackets twice. Well, the compiler knows from the left-hand side that this is going to be an array list of strings, so it could just substitute that for you on the right-hand side. So you can just type an empty diamond, empty pointy brackets, and the compiler will fill that in for you. We couldn't infer the pointy brackets themselves because without the pointy brackets, that actually has a different meaning as a thing called a raw type. And so we're kind of stuck with that, but at least it got less verbose in 7. In 8, when we introduced lambdas, you can write a lambda like this. You can write the type of each lambda parameter variable, in this case string s, but you don't have to. The compiler can infer it, and you can just type s arrow s.length. Now sometimes it is useful to write out the type of a lambda parameter variable, but you don't have to. More type inference. In Java 10, we introduced local variable type inference. Local variable type inference is for cases like this. We've all written this code. Buffered reader equals new buffered reader, blah, blah. Yeah, okay, fine. And yeah, sure, your ID can partly write that for you, but come on, do I really need to even read buffered reader twice? So in 10, we have the var keyword. Technically it's a pseudo keyword, don't tell anybody. So you can say you can type var reader equals new buffered reader. The compiler has enough information on the right-hand side of the assignment to understand, oh, yeah, it's a buffered reader. So it effectively inserts that on the left-hand side. So it is limited to local variables. That's why it's called local variable type inference. Get the hint? You can't use this on fields. You can't use this on method parameters or lambda parameters. And we're not turning Java into JavaScript. This is not dynamic typing. This is not saying that reader could be anything. Reader is, in scope here, it is going to be a buffered reader for the rest of this local variable scope. There's no doubt about it. It's not dynamic typing like in JavaScript. It's just better static typing and much less keyboard typing. So that's a good thing. And also a lot less reading for your eyes, which is even better. You probably, if you're in the habit, as I'll admit I am, of tending to use short variable names, you might want to consider using longer ones. If you have an extended example like this, where you've got a URL, you're opening a connection, you're wrapping a scanner around it, it looks much nicer with var. But if you just use variables u, c, and s here, then 20 lines later your code may be less than clear. So local variable type inference, the var keyword in Java 10. The details are in JEP 286 if you would like to check that out. All right, let's move on. Oh yeah, there's JEP 286. Let's move on to another thing. So Trish told me she talked about switch expressions. Everybody remember? Does anybody want me to talk about switch expressions? No? Skip? Show? Oh, jeez. Got the same guy. It sounds like the same guy saying yes and no here. All right, I'll go through this quickly then. Doesn't take long. All right, so suppose we've got days of the week, enum, days of the week, Monday, Tuesday, et cetera, et cetera. And for the sake of this little exercise here, we want to compute the length of the name of each day. Now, if you're clever, the clever way to do that, of course, is to just invoke toString on a day of week object and compute its length, right? But for illustrative purposes, assume we're not going to do that. Instead, we're going to write a switch. So we have a num_letters variable. We switch on a day of week object. We have cases Monday, Friday, Sunday. Num_letters is 6. Break Tuesday, Thursday, Wednesday, etc. Wednesday, sometimes a source of really obscure bugs because it is the longest name. All kinds of stuff can go wrong here, right? You can forget a break, and something will fall through. You can forget to assign to num_letters. You could forget your default, or maybe you fall into the default because you forgot the break ahead of it. As Brian Getz likes to say, this isn't the language helping you out. This is the language daring you to make a stupid mistake. And if you think about it, well, we're just computing an expression, so let's write it that way. And in Java 12, you can. You write switch as an expression. You can put it on the right-hand side of an assignment statement. You can embed it in a bigger expression if you really want to. We borrowed the arrow syntax from Lambda, so that's how you indicate the value of the expression. And as an extra special bonus, the compiler in some cases can infer, can deduce that you've covered all the cases. So you don't need to provide a default. If you need to provide a default, the compiler will tell you and will insist that you do so, but you don't have to. So switch expressions are in Java 12. The details are in JEP 325. Switch expressions are a preview feature. What does this mean? It means they are in the spec, they're implemented by the compiler, so the VM will run them and everything else, but they're not enabled by default. They're 99% baked, but we wanted to leverage one of these 6-month release cycles to get any last feedback we can, because once we add something to the language, it takes forever to take it out. We pretty much consider anything in the language etched in stone. So if you want to play with switch expressions in 12, you need to use this command line option for at both compile time and runtime. either on the command line or in your POM XML or whatever your build system uses to enable it. And if you see something funny, you have feedback for us, please send it in because we want to make these final in Java 13, which is due in mid-September, which means we need to be making any last decisions real soon now. Okay, let's move on to features that are not yet in any early access build. Another kind of code that we've probably all written. You've got an application, you need to spew out some HTML, so you have a string constant that's basically some HTML, and you wind up writing a bunch of double quotes and ending lines with pluses and quoting things, and oh yeah, you've got embedded quotes inside your string constant, so don't forget to quote those with backslashes, and so on and so forth. Yeah, this is kind of annoying. Can we just have multi-line strings, please? Yes. So we're working on multi-line string literals. This is a surprisingly complicated feature to design. We actually almost had them in 12 as a preview feature, but pulled them at the very last minute due to valuable feedback that we received. This is the current proposal. It's not in any early access build yet. We're borrowing, the syntax may look familiar from Python and other languages, triple double quote at the beginning, triple double quote at the end. If you need a triple double quote in the middle, then you'll have to use a bunch of backslashes, but the chances of that are fairly small in practice. Now, if you look at this carefully, the value of the string constant will include a bunch of white space from over here that you included in order to have your Java code be indented properly. You probably don't actually want that in your string constant. So we're going to add a handy method to the string class called align that will figure out what the common subsequence of leading white space is and strip that, so you just get the HTML indented naturally the way you expect. So we're aiming that for Java 13 in a JEP not quite yet written. That will also be a preview feature in 13. Maybe we'll see what happens. Code close for 13 is in about a month, so we'll see what happens. All right. Another kind of code that a lot of us write all the time. Say we have a point. A point has an x and a y value. We have a constructor. We have accessors. Is there anything missing here? What's missing? Speak up. Equals hash code and toString. Oh yeah, I got to write those too. Yeah, and you can do that, or your IDE can do it for you, and then you go and change it maybe a little bit. But then 2 years later, you come to maintain this stuff, then you have to go read that, read equals hash code and toString again, and make sure they're actually right. All of this code means, well, it's easy to cut corners, and cutting corners leads to bugs, and bugs lead to unhappiness, and we know the rest. And if you look at it, the amount of encapsulation here is actually, is extreme. We don't need any of the encapsulation that this class is providing us. We've got an X and a Y. They're perfectly visible. There's no reason to go around hiding them. There's no secret here. We just need a way to say this class is a transparent container for some data. So we can do that with another feature we're working on called records. You just type record, point, double X, double Y, semicolon. You're done. That's it. And that stands in for all of this code that's now dimmed out. Records can replace all of that Pojo code because sometimes data is just data. So I have a request. I'm hearing some conversations. If you want to share, you can come up on stage. Otherwise, please keep it to yourself or leave the room. Thank you. You can customize records if you want to by adding some stuff. For example, you could, if you want a different hash code algorithm than the one that's provided, you can write your own. Maybe you want to have compute the norm value of a point, so you can add a norm method. You can even provide your own constructor, so you can do things like ensure invariance of data that's coming in. What you cannot do is add more state. You cannot add more data, because that would violate the invariant that a record is a transparent holder for data. So all of your data has to be declared up front at the top. Another thing about records is that they are immutable. You cannot modify the value of a record object once it's been created. But that's okay. If you really need a mutable one that you can modify, well, then just go write a class, have your ID write the class like you always have. We do have a prototype implementation of this, but it's not in any early access build yet. Okay, one last item from Amber, and then we'll move on. Suppose you have an object, and it's say it's going to be an integer or a double or a point, the thing that we just saw, and you want to create a nice little formatted string that describes its value. You could write code like this. The format method takes an object, it initializes our string s to unknown, and we go through. If ob is instance of an integer, whoops. Sorry. If ob is instance of integer, then we cast ob to an integer, we stick in a variable I, and then we do string.format of our little message. We do a similar thing here. If it's instance of double, if it's instance of point, then we extract p.x, p.y, we make our little string, and finally at the end we return s. And it looks like I forgot a closing brace. Oh no. Weird. Okay. Pattern matching lets us make this more compact, lets you express more clearly what you mean by doing this. So what are highlighted in orange here are things we call patterns. A pattern combines two things. It combines a type and precondition test with a bind operation. If the test succeeds, then it binds a variable, and that variable is in scope for the next bit of the if statement in this case. So here ob instance of integer I. If ob is an integer, then it will be cast to an integer for you, bound to I, and then you can just use I in that arm of the if statement in the natural way. You don't have to cast it yourself because, well, the compiler can figure this all out for you. What's really cool is you can also use patterns to deconstruct things. So a point has an x and a y. We saw that in the record declaration previously. If ob is an instance of point, then this will extract its x and y values, assign them to the variables x and y, and then in the remainder of this expression, oh, mark. Pretend those aren't there. It's just... I love Apple Keynote except for one thing. You can't extract code and run it and test it in a natural way. So I apologize for the mistake on the slide. Patterns play well with switch expressions. So we can bundle all this up into a switch expression, and this is much shorter than it was, much clearer, and much less boilerplate. Okay, so that's a selection of features from Amber. Let's now move on to something completely different, and Loom, continuations and fibers. Can we switch to this machine, please? It's the same slide, so sorry, it might be. Okay, good, we've got the right machine. Tricky. All right, so what is Loom all about? Let's just look at some code. Demo Loom. So here I have a 2-day-old build of the Loom repository from OpenJDK. Built this just a couple of days ago. Let's pop into JShell and poke around a bit. So fibers are addressed at the expense, at the cost of threads. Threads are great. They've been great for Java. One of the things that Java kind of snuck into more popular styles of computing is threads. Lots of people needed threads. They didn't necessarily know they needed them, but they did. And Java brought threads to a lot of people in a way that was fairly easy to understand. So we can make a thread, new thread. I'll use a little lambda here. We do that, we've got a thread, we can run it. What happens? Ooh, it prints hi, yay! So thread object, that's really easy. And of course, you can have thousands or millions of these, and it all kind of works. But threads come with a lot of baggage. We can ask JShell, well, how much baggage does it have exactly? A thread object has all these methods. Now, yes, a handful of these are inherited from Java Lang object. You're stuck with those. But there's a bunch of stuff here that's of a somewhat questionable nature. There are thread priorities, which in most implementations mean nothing. There are thread groups, which have almost no uses at all and are an extraneous abstraction, unfortunately introduced in the early days that we can't really get rid of. Threads have a thing called a context class loader. In the pantheon of questionable, if not bad, design decisions from the early days of Java, context class loader is on that list. It's lower than serialization, and it's lower than finalization, but it's on a list of things we kind of wish we hadn't done then. Most of all, a Java thread corresponds to an operating system thread. That's convenient because it means the operating system does all of the work, but it means that Java threads are expensive to create. It means that it's expensive to switch from one Java thread to another, one operating system thread to another. It's typically thousands of instructions to switch from one thread to another. That can be a long time. Because they're so heavyweight and expensive, in order to get high performance, people who write things like web servers tend to go with non-blocking I/O techniques or asynchronous I/O techniques. These are really hard techniques to use properly. So you will find experts who are writing web servers doing it, but then the applications that they're serving typically won't use non-blocking or asynchronous I/O. They're just written in the normal sequential way. And so web servers, server hardware winds up being underutilized because you've got all these things happening in threads and there's no way to make them more efficient. So a fiber, as the name suggests, is a lightweight thread. Let's make ourselves a fiber. We can say fiber.schedule. I'll do out println. And so one difference in the API is with fibers, you create them and they're scheduled to run immediately. So it prints hi, and then it comes back and prints the value of the fiber object. And its toString note says no carrier thread. And what that means is right now, this fiber is not associated with a carrier thread. You could have a fiber that does some computation, it's bound to a thread for that time, then it yields, and if you examined it and asked for its toString, it would say no carrier thread, and then when it's running again, it would say carrier thread and give you the ID of the thread. So fibers allow the Java runtime to dynamically map your workload to operating system threads as you go. Because the switching between fibers is all done by the Java runtime system, switching between fibers can be done in 100 or 200 instructions. It's really, really fast. And fibers themselves are much smaller objects. A Java thread comes not only with a kind of biggish Java heap object, but there's also a thread stack allocated out of heap that I think by default is like a megabyte or something, so that's big. A fiber in the prototype implementation is on the order of hundreds of bytes. So if you want to have 1 million fibers in your Java heap, it's not a problem. Fibers are also simpler than threads. Here are all the methods on our little fiber object. Aside from the ones that you get from Java Lang object, what can you do? Well, you can cancel a fiber. You can ask if a fiber's alive. You can ask if it's been canceled. You can wait for it to terminate, and not much else. So let's look at a more real example. I'll drop into my favorite IDE, namely Emacs. Java, main Java. I'm going to do a little benchmarking here with a hypothetical REST service. So this is using JAX-RS, and answering on the path REST. We have a little method called sleep. It takes a parameter, a number of milliseconds. You give it some milliseconds, or it defaults to 100. And what does it do? Well, it sleeps for 100 milliseconds. So this is just a very simple simulation of a web service that is written sequentially. It does something for 100 milliseconds. There's no non-blocking or asynchronous I/O going on here. So let's run this with threads. Make threads. I'll bundle it up into a makefile. We run Maven, of course. So this is running inside the Jetty embedded web server, and I'm using the Vegeta load generation tool to hit that web server at 1,000 requests per second, first for a 5-second warm-up and then a 10-second run, and we'll look at a graph when it's finished. There we go. Oh yeah, Firefox certificate problem, thank you very much. Demo. Graph. Okay, here are response times for that sleep service with threads. Starts out, well, maybe not too bad. Okay, yeah, 300 millisecond latency for 100 millisecond service, not great. But you see, after the system's been running for a while, it gets really bad out here with response times of a second and a half in some cases. This is not what you want to see in production. So let's reset that. Cool thing about Jetty is you configure it not with a pile of XML or JSON or whatever. You configure it by writing Java code. And we can configure it to use threads simply by giving it a custom thread pool. So it has its own little thread pool abstraction. And all we need to do is go down here and override the execute method, which by default will create a new thread and run it. And instead, we're just going to execute whatever needs to be executed on a fiber. And let's see how that goes. So no actual change to the code, just one change to a command line option. Dum, 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 dum. And okay, it didn't crash, looks like. Good. Let's reload that. And you see that fibers are actually doing pretty well. So there is an initial warm-up period. I'll zoom in on this segment. There is an initial warm-up period while the code gets compiled and Hotspot does its dynamic compilation thing. But after it's been running for a while, the latency goes down to usually just barely over 100 milliseconds. And so almost all of the latency is taken up by that sleep, and the overhead of switching from one fiber to another is hard to measure. I mean, it's showing up there, but it's far less, certainly, than it was with threads. So that's a big improvement. Fibers are not just for avoiding non-blocking I/O, although they're obviously very good for that. They open the door to a bunch of new techniques, things like channels and data flow and actors. And the cool thing is these will all be implementable as libraries on top of the Java platform. They're not things that we actually have to engineer into the JVM, into the language, whatever. In passing, I did mention continuations. Continuations are the lower level JVM mechanism upon which fibers are built. Continuations are useful for a bunch of other things like generators with yield and so forth that we might exploit in the future. But we'll see. And for now, continuations probably won't be exposed in the public API. But they are another example of Java borrowing well-established concepts from other languages. Okay, let's move on to Panama. So, invoking native code in Java, how many people have actually written JNI? Okay, a fair number. How many people enjoyed it? Okay, good. Me neither. It's kind of painful. Invoking native code, interacting with native data is a pretty clunky thing in Java. JNI is painful to write. It's slow to boot. Well, I mean, it's slow to run. Slow additionally. You have to write C code, compile it into a native library, load the library, and all that. For native data, you can use JNI or you can use direct byte buffers, but those get kind of clunky too with any sort of sophisticated data format. Panama is a brand new for Java approach to interacting with foreign functions and foreign data. Again, this is not high level. This is not a new idea. Other platforms have certainly done this sort of thing, but now we're trying to do it for Java. So let's take a look at some code. Here I've got another 2-day-old build of the Panama repo. So canonical demo of native interaction is, let's look at standard Unix library call, get PID, get your process identifier. Really simple. It takes no arguments, and it returns a PID-T, which is really just an int, and that is your process ID. How hard can it be to do this from Java? Well, with JNI, you have to write a bunch of stuff, and it's all boilerplatey and ugly and easy to get wrong. Let me show how you do it. I'll show you how you do it in Panama. So Panama has 3 components. One is a tool called JExtract. Remember, from the man page, we learned that to use this, you need to look at unistandard.h, that header file, and some stuff in systypes.h. That's effectively the API definition here. So what we can do is we can type JExtract, user include unistandard.h. Since it's a prototype, I have to do this. You pay no attention to the man behind the option here. And I'm going to generate some classes from it. So from unistandard.h, we're going to get a bunch of Java classes. They're actually all interfaces. These are compiled using the LLVM front end. These are compiled from those actual C header files into a Java representation of what's inside. And if we look inside one of these, in particular, if we look inside unistandard_h.class, we see, oh, familiar looking stuff. All these int constants defined in unistandard.h. It is an interface, so these really are constants, and abstract shows up just because JavaP is being as correct as it possibly can be. We go through here and look, and we find, oh, look, there's getPID. So we have an interface here that was generated from the C header file. What are we going to do with it? Well, at runtime, what we're going to do is, import it. We're going to import the Panama API, which is most of it is a Java API that models C data types. So it has, there's a pointer type in there, and it's parameterized and other memory-ish looking things. To get the process ID, we will invoke a static method in the Panama libraries class to do a binding. What that binding does is says you're saying, okay, I've got this unistandard_h interface that represents the Unix library thing I want to invoke. I pass it a method handle lookup object for my current execution context, and what I get back is an object that implements the unistandard_h interface. And inside that object is a getPID method, which I can invoke. And just for sanity's sake, I will also invoke the Java API that we already have that returns the getPID method. So let me just run this. Classes, getPID.java. No, I'm not compiling this because we can now launch single file source code programs directly at the runtime, with the runtime. We run this, it does its thing, and it gets the process ID. And I never actually had to look at any C code. I never had to write any C code. I didn't need to compile a .so file and remember where it was and tell Java how to find it. So that's the quickie demo of Panama. The thing to say about Panama is everybody will benefit from it, but most people will benefit from it indirectly. It's really meant it's really meant to be used by people who maintain native libraries. So, for example, people who maintain things like OpenGL or TensorFlow, they're experts in how those libraries work. They can use Panama to digest their own C, C++ header files and provide to you an easy to use Java API that was not derived from those header files. But the fact that they can use that step makes their job much easier. As to performance, Panama is currently slightly faster than JNI, but we have some code still in the works that's actually looking good. It will probably be around 4 times faster in the end. All right, let's move on to the last item, Valhalla, value types and specialized generics. Why are we working on Valhalla? We've been working on Valhalla for a while now. It is a big project making very, very deep cuts in both the language and the virtual machine. Well, the answer in one image is this. Today's processors are vastly different from those we had in 1995 when Java was a new thing. The cost of a cache miss has increased from between a factor of 200 to a factor of 1,000. It can now take forever if a memory access misses in the cache. Why is this relevant to Java? Well, being an object-oriented language, we have lots of objects around. If it's not a primitive type, then it's an object. If you have objects, then you have pointers, and objects point off to other objects, and every time you chase a pointer, that's an opportunity to take a cache miss and have your processor sit there for hundreds, thousands of cycles waiting for the slow, pokey memory system to return some data. Another thing about objects is objects are heavyweight. Every object has, objects have identity. You can synchronize on any object, and people do this. I've seen industrial applications where people were synchronizing on the string constant y, capital Y, and they had gazillions of these string constant y's that they were synchronizing. I'm like, oh, really? Anyway, so this gets really painful, especially when you're dealing with a lot of data, as you might be in machine learning, or you're trying to do image processing or something. So we're trying to address that, and we think the missing abstraction here is value types. In Java, there's no way to declare a pure data aggregator. I mean, sure, I showed you records. Records are pure in a sense, but they still wind up being objects, right? What we want is a way to say, here's a thing. It's just data. There's no state. It'll never change. You're never going to synchronize on it. It doesn't need to be in the heap. If you can allocate it in registers for its entire lifetime, do that. Right now, we can't do that. As John Rose likes to say, if we do this right, you'll be able to code it like a class, but it'll work like an int. So that's where we're trying to go with Valhalla. Let's switch to Valhalla demo. Here's the version. Yep, that's the right one. And once again, let's look at a little code here. Complex numbers, kind of like points. Same idea, right? This could be records in some future version. Yeah, public class complex. You've got real and imaginary. You've got a constructor. You've got accessors, and you've got add and multiply. If you're in benchmark mode, you have complex numbers. How do you benchmark them? You multiply matrices. Yes, of course. Perfectly natural operation. So we're going to do some matrix multiplication here. I've set this up as a benchmark using Alexei Shiplev's very fine Java micro benchmark harness. So there's some annotations here telling it how to run it. We have two complex matrices represented as arrays of complex objects. We populate it with some random numbers. We set things up, and then of course we have the matrix multiplication itself. Standard cubic algorithm, walk across the rows of one matrix, columns of another, do the pointwise multiplications and sums, and boom, you get a result. Okay, let's run this. Maven makes another guest appearance. Okay, so I'm going to do three warm-up iterations here, and then some actual test runs, and this is taking about 4 seconds per matrix multiply. And my laptop is not getting warm or really working very hard at all. Iteration 1. Yeah, about 4 seconds per matrix multiply. If you look at the GC alloc rate norm, that's how much memory is being allocated per multiplication, and that's almost 4 megabytes just to multiply a couple of 500 by 500 Matrices. All right, that's not very impressive. Okay, that's a little hairy. Let's look at it in Emacs. Okay, we have this warning from Alexei. Pay attention to that advice. It's very good advice. Multiply is taking almost 4 seconds each round. Let me just mark that. We're allocating about 4 gigabytes for each one. And then another interesting metric here, which I'll highlight, is the instructions per cycle. So the processor in this laptop is an Intel Skylake processor. It's capable of retiring 4 instructions per CPU cycle. It is retiring barely more than 1. So this number is telling us that the processor is mostly just sitting around twiddling its thumbs, waiting for the memory system, because it's chasing pointers from those arrays in the matrices off to all the complex number objects. And of course, it had to allocate a bunch of complex number objects because every complex number is an object, because, oh, it's object-oriented. Everything's an object. Great. Well, not really, as we're seeing now. So what we're going to do is, I'll go into this complex class, and I'm going to add one keyword, V-A-L-U-E. I'm going to make this a value class, which looks like a class, but works more like an int. And let's run our benchmark again. Recompile it since I changed the source. We do some warm-ups. Ooh, it's taking 366 milliseconds per operation. So that's quite a bit faster. Cool. I did this talk 6 weeks ago, and it was faster than that. So I mean, this is live prototype code. It changes every day. And we're allocating only about 4 megabytes, not gigabytes, 4 megabytes per matrix multiply, because the only allocation that's happening is for the result matrix. We're not having to allocate a bunch of intermediate complex number objects as we go. So let's go back into Emacs for comparison. I'll put the old numbers at the top and load this in at the bottom. Okay, new results at the bottom, 338 milliseconds per operation. If we do a little quick division here, it's about 11 times faster than the other version. It's allocating a lot less, and instructions per cycle, it's retiring almost 3, so it's making much better use of the processor. 4 would be ideal. Being able to do almost 3 is certainly way better than barely more than 1. So that's a quick look at Valhalla and value classes. Once Valhalla is done, even if you never use it, you will benefit from it, because Valhalla will enable people who write libraries, not just the libraries in the JDK, but people who write libraries everywhere, to redo their data structures to make them much more efficient. So everybody will benefit, even if not everybody uses it directly. All right. So that was Valhalla, Amber Loom, Panama Valhalla. This is a really exciting time for Java. Our R&D pipeline is richer than it's been in many, many years. Starting with Lambda, continuing with Jigsaw, and now with these projects. There's a really bright future ahead here. I hope that you'll take a look at some of the early access releases, send us feedback, and help us move Java forward. If you'd like to take a look at the early access stuff, it's all on jdk.java.net right now. We have EA builds for 13, for Panama, for Valhalla, for some other things. I'm told there will be an early access build for Loom probably in the next month, maybe month or 2 months. There are 2 minutes left for quick questions. Otherwise, you can catch me at the Oracle booth afterward, or in the hallway whenever. I'll be here today and tomorrow. Yes, sir?
Following JDK 11, when is the next long-term support version?
3 years. Long-term support releases are every 3 years. Any other quick questions? Sir?
The value and the record are going to work together.
Yes, values and records will work together. You will be able to type value, record, complex, real, imaginary, done. Okay, 1 minute. Race is on. Yes? Sir, what? I'm sorry, I can't hear you. Future of threads? Well, what's the future of the class path? Are we ever going to take it away? No, of course not. No, threads will be there forever. But I think gradually we will encourage people to migrate off of them. There will be some big performance benefits to be gained by going through that migration effort. Hopefully in the future, people will not be writing in threads by default. And by the way, with a fiber-oriented computation model, the need for these complex reactive frameworks kind of goes away. So the little screen here is telling me time is up. Thank you very much. Oh. And don't believe anything I said.